Okay, gang, welcome to CSC470, computer graphics. If I've got the right day of the week and the right time, which would be good if I did. It would be bad if I didn't. So today what we're going to do is we are going to talk about, last time we talked about display coordinates, or actually display devices, and I remember some of you, Eric, if I'm not mistaken, has tried to convince me that 144 frames per second is the new necessary standard. So I still think 30 or 60 is fine. Call me old school. So we looked at display technologies for a little bit. Then we talked about how polygons are stored inside computer graphics systems. And then we talked about projecting three-dimensional images into two-dimensional images, which is, of course, what we ultimately have to do. Why don't I share the syllabus so you guys can see what we've done and where we're going. Monday we talked about history, progress, and rendering humans. And I fooled some of you into thinking that Grace Kelly, the actress, was actually computer generated. I'm sorry if that was an evil trick, but I enjoyed doing it. I think it made a good point, which is that computer graphics are getting to the point where it's not always possible to tell the human from the computer-generated imagery. Then last time, like I said, we talked about display hardware, polygons, and perspective projection. Today, we're going to talk about drawing coordinates. Basically, what that means is getting from our projected imagery, how are we going to get that onto display hardware? There's a little step we're going to have to do there. And then we'll go on and start talking about the major things that you can do with two-dimensional objects. To start with, the transformations, and there are three of them, main transformations. One's called translation, one's called scaling, and one's called rotation. We're going to get through translation and scaling, and we may start on rotation, that's fine. Also on Monday, we will talk about, this upcoming Monday, we'll talk about three-dimensional transformations, and at that point, you will have had everything you need for me to give you assignment 1. I'm also going to give you a Python framework for assignment 1, and I'm going to give a demo of assignment 1 running with my code. Obviously, I'm not going to give you my code. Well, the framework is probably at least 50%, maybe 75% of the actual code of the program. So the way this class goes, assignment 1 and assignment 2, which by the way will be given almost immediately after we get back, because there's very little material I have to cover between assignment 1 and assignment 2. But assignments 1 and 2 are pretty straightforward. They are the easy assignments. You need to rack up points on those, because assignment 3 and assignment 4 are quite difficult. Assignment 3 and assignment 4 are quite difficult. They're not doable. A lot of students get them, but you need to plan on, you're going to probably spend 20, 30, 40 hours on 3 and 4, literally. You need to book about a week's worth of effort full time for assignment 3 and assignment 4. Yeah, they're neural network difficult, Logan, for those of you who had, yeah, Eric, about 30 hours each on 3 and 4. If I look at the past numbers for students who got them, 3 and 4 are very hard. But they're very rewarding because they're really dealing with things like hidden surface removal to make your polygons look solid. And assignment 4 is adding shading to get rid of to make polygonal surfaces look smooth, basically. So Yeah, anywhere from 20 to 40 hours. I don't have many people who finish them in less than 20. Almost nobody goes over 40, but that gives you an idea. The other thing is you need to really put in effort on assignment 1 and assignment 2. I'm trying to tell you guys, don't get overly confident when you figure out, oh, Mike gave me most of assignment 1 and all the formulas are in the notes, so that was a breeze, right? And assignment 2 is just a moderate extension of assignment 1, so I don't want you guys to get to thinking, oh, this doesn't take any time at all. We made out like bandits here. There are no exams and the program assignments are easy. 1 and 2 are designed to be easy to get you started. I'm going to give you a lot of material to get you going. 3 and 4 are more difficult. You'll have all the equations. We'll go through all of the algorithms. It'll all be laid out in the notes, but it'll be up to you to translate that into code and to debug it. And then the last assignment, assignment 5, deals with ray tracing. And again, on assignment 5, I'm going to give you a go-by program that'll again do, maybe 50%, 75% of the effort. So 1, 2, and 5 are not as nearly as taxing as 3 and 4. And yes, Eric, as I was trying to say, but falling by the wayside like I usually do, you need to put a lot of effort into 1 and 2 to make sure you understand them thoroughly, because everything builds on everything else. And students frequently run into problems on assignment 3 in that they get it kind of working, so they get partial credit on 3, but unfortunately, to even start on assignment 4, you have to have your code for 3 rock solid. So students start falling behind there. They didn't put in enough effort to really get 3 complete, and so then when they go off and they start on 4, you can't do 4 without 3. 4 literally builds directly on the code 3. So now that I've properly scared you, sorry about that, but I want everybody to know, because I don't want anybody to get stuck, right? If you're interested, I have all of the notes up through probably next Wednesday and more are in the handout that's on. It's called Lecture Block 1. That's on Moodle. I keep updating that as I add new material and move material around, but the material through assignment 1 is solid. That's not going to change. If I find some typos, maybe tiny minor changes. But basically, all of the material through assignment 1 is now out on Moodle. If we were to look on Moodle, let me see if I can shift over to that. If we look at Moodle, under the under assignments, there's now assignment 1. All of the details. We're going to go over that either on Monday or Wednesday, probably next Wednesday. But you know enough already to get started on assignment 1. And also there's a Python framework. Well, that didn't help out too much. There's a Python framework that's out there that I'm going to go over next Wednesday, go through it thoroughly. And basically what you're going to do is you're going to be plugging in equations that we've been covering through our notes, through our lectures, into that assignment 1 framework. So again, if we look at the syllabus again, I'm officially going to, today is Friday, officially I'm not going to give out the assignment or go over the assignment until either the end of class on Monday or much more likely on Wednesday, right? Well, you look, your project update for your group is due that Friday, so that means Thursday you're going to be working on your group project stuff. And then we come back after Christmas, there's a lecture on Monday, and then your assignment is due Tuesday. So while there's, 3 weeks of calendar time, there's really less than a week of your in-school time. So again, I'm encouraging you guys to get started early. Most of you, if you're familiar with Python, if you've played around with tkinter, then how many of you have not seen tkinter before? The graphics package for Python in chat. Is there anybody who's not seen tkinter? Well, let me ask it the other way, since there's all silence. How many have you used tkinter before? A simple yes. Okay. I'm getting some yeses. Okay. Okay. Somebody's asking about Dr. Cherry's lecture. You're thinking about the wrong class. Dr. Cherry does not lecture in 470. Dr. Cherry and Dr. O'Neill lecture in 405. Okay, so yeah, it looks like everybody used it. So that's good. So you all know Python. Most of you, if not all of you, have used tkinter. So you guys can go ahead and get started on the programming assignment now. There's no reason to wait till next Wednesday. Okay. All right. Okay. Are there any questions about what we're going to be doing for the rest of today and what we're going to be doing next week, including the programming assignment and when it's due when we get back? Okay. Okay, good. All right. All righty. So we're cooking with gas, as they say. So we're going to get rid of this. And we're not going to need to see Moodle anymore right now. So let's go and get into the lecture notes. So the lecture notes, these are the lecture notes that are up on Moodle, and I think I refer to them as block 1 lecture notes. I'm sorry. The screen on my laptop is this laptop is awesome for hold on a second. Did I ever start the recording today? Anybody remember if I started the recording? Yeah, it says recording. Okay, good. Thank you. I haven't had my coffee either, and so Andrew, so don't feel bad, and that's why I'm half out of it. I was working on notes for my other class until about 2 in the morning last night. So, how do I move this so that I can get? Okay, that's how I move it. Okay. So, so yeah, when I say that all the lecture notes are up there, these are the lecture notes we covered yesterday. Well, I've got the lecture notes we're going to cover today. I've got the lecture notes we're going to cover on Monday, and it goes all the way through some handwritten stuff, all the way through. By the time you get to page at the bottom of page 14, that's everything you need to be able to do the programming assignment. And these equations, all of the equations tend to be in bold, so it's easy to find those equations. So even if I haven't covered it, it's easy to go in there and crib those equations and fill them in. Okay, so you guys could go ahead and get started over the weekend or Monday or Tuesday of next week, so you don't push it all the way off to Wednesday, and then you have to kind of worry about it over the Christmas holiday. Unless you want to work on it over the Christmas holiday, that's good. Okay, so anyway, we did displays last time. We talked about older displays that used a 4:3 outline, and then we talked about newer displays like HD and 4K that used a 16:9 orientation. We talked about frame rate. I've been kidding Eric for 144 frames per second. Eric, I hope you don't take that personally. I'm just messing with you, dude. But yeah, we talked about the different frame rates and what that does to how many bits you have to manipulate per second. And it's gargantuan, and that's why speed are the 5 most important things in computer graphics. Oh, and did I mention speed is the 6th most important thing in computer graphics. After the hardware, we talked about polygons. Polygons are flat, multi-sided figures. We don't allow the edges to cross in this class. If you put, the 7th is also speed, John. If we look at an object, there's a hierarchy to things. An object is composed of a collection of polygons. This pyramid has 5 polygons: a front, a back, a left, a right, and a bottom. Don't forget the bottom. And so a pyramid is a collection of polygons: front, back, left, right, base. And then each polygon is a list of points where you draw a line from the first point to the second point, from the second point to the third point, from the third to the fourth, fifth, et cetera, all the way from the last point back to the first point. And if you're doing triangles, there will always be 3 lines that you draw, from 1 to 2, from 2 to 3, and then from 3 back to 1. When I talk about the fact that I'm always updating these notes, if you made a copy of these notes from last time, I had forgotten to put down base. As I was going over things, I saw that I'd left it out, so I added it. So always download the newest copy of the notes before you study them, because as I find little things, I do go back and make changes. Okay, so we can't really look at a 3-dimensional, well, in the real world, if you've got 2 eyes, you can look at 3-dimensional objects in the real world, but all of our display technologies are actually 2-dimensional display technologies. So we have to have some way of getting a 3-dimensional pyramid onto a 2-dimensional display. And this is an example of what we need to do. You look at this and you still go, okay, that looks like a pyramid to me, especially if you mentally ignore that back line that you wouldn't be able to see. You go, yeah, it looks like a pyramid. I'm kind of looking at it kind of like down from a 45-degree angle from the front of the thing. And so we need a way of doing that. And what we do is we use perspective projection. These are the first equations that you're going to need in your programming assignment. There are equations for perspective projection. What they do is they take in an x, y, z point, x, y, z, and they compute a new x, perspective x, a new y, perspective y, and a new z that we're not going to play with right now, but we're keeping around to keep up with the relative depth of that point, the relative distance that point is from the viewer. So z exists. We're not going to actually play with it right now. X and y are the most important things. So what's the input? The input is x, y, and z. What's the output? X perspective, y perspective, z perspective. And if you're talking about just visualization and not worrying about the depth right now, the inputs are x, y, and z, right? And the outputs are perspective x and perspective y. Okay. Now, we talked briefly last time about how these equations are generated. By the way, I see that I just lost video. Hopefully it'll come back. Again, you should have these lecture notes from Moodle in front of you as we talk, so you should be able to see what I'm talking about, even if we lose video. So, looking at the figure on the bottom of page 3, you see that we've got an X, Y, and Z point in three-dimensional space. Well, I can't show you that point in three-dimensional space. So what I'm doing here is we are looking from the top down. We're looking from positive X. Think about a coordinate system, right? X goes off to the right, Y goes up to the top, right? So we're at the top at positive Y, looking straight down to the origin. If we do that, what are we going to see? Well, we're going to see the x-axis and we're going to see the z-axis. So those are the two axes that we're going to see. I'm still here. I'm just wondering if this is still recording. Anyway, does it say if it's still recording on you guys' end, by the way?
It still says
Hello?
recording over here.
Okay, awesome, great, thank you. And hopefully everybody's gotten their lecture notes up by now from Moodle. So again, I'm at the bottom of page 3, I'm looking down. Where you see X, actually that is the XY plane, okay? It's the XY plane. Hold on, I'm getting video back. 1 second. Let me reconnect my audio. Okay. Sorry about that. So this is actually the XY plane. Remember, center of projection, that's me or you. That's the viewer. And the viewer is looking at a display screen that we have set up so that it matches mathematically the XY plane. Okay, so from this center of projection, if I want to look at this point in three-dimensional space, well, it passes through this pixel on the display. It'll have some X and Y component to it. So how do I know where this XY is actually at? Well, I'm given the vertices of the point that I want to project. I'm given an X, a Y, and a Z, right? I'm also given a distance that I am in front of the screen, distance to the center of projection to where we are assuming the viewer is at, okay? And so because of similar triangles, because of essentially the tangent function, which is the opposite, which in this case is X, the X dimension, over the adjacent, which is essentially D plus Z, right? X over D plus Z must be the same as X perspective projection over D. So that's where this comes from. And then a little bit of algebra, you can just move the D to the other side, right? Multiply both sides by D, and you get the answer. X perspective will be the D that you're given, the X for the input, and the Z that you're given. So all of the things on the right-hand side you're given, and that lets you compute the perspective projection point. Well, at least the X component of it. We have to do the same thing for the Y perspective point. So now then, this is a side view. So I'm looking from positive X. So earlier, I was actually up here looking down, right? Well, now I am at positive X. So if I go back. So this next one is I'm going to be at positive X. I'm going to be here, and I'm going to be looking back towards the origin. Okay? So now I'm looking from positive X to the origin. All right, this is still the XY plane. Okay, But now since I'm looking from the side view, I can get the other dimension. I can get the y dimension, and it is exactly the same sort of thing. Y over d plus z is y perspective projection over d. You multiply both sides by d, and you get this equation. So the equations are very easy to derive. How do we use the equations? Well, if we've got an object in three-dimensional space, where each of these is a vertex, when you've got vertices, we talked about how we store polygons, I can project these 1, 2, 3, 4, 5, 6 vertices, and then just draw lines between those vertices. And because these are linear equations, straight lines go to straight lines, and so you don't actually have to draw the object in three-dimensional space. You project the vertices, and then you draw the polygon in 2D flat space, but it comes out looking exactly like the 3D image would if I had taken each of these many, thousands and thousands of points for each edge and projected each one of them onto the screen. I would have gotten exactly what you get by taking the 6 points, projecting them, and then drawing the polygons in 2D space. Does that make sense? Yes, no, maybe, sort of, Mike. Remember what I said the first 8 things about computer graphics were? Speed, 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 speed. Well, I've just saved you orders of magnitude here, maybe thousands of times of work by saying you don't have to take every little dot on every edge in three-dimensional space and project it. Just project the vertices, there's 6 of them in this case, and then just draw the lines over here on the screen. And as long as you are respecting the definitions of your polygons, right? Drawing a line from the first vertex to the second, from the second to the third, and from the third back to the first, you're going to get the exact same image that you would have gotten if you had taken absolutely everything and projected it. One other thing that we covered last time, remember, always list your polygons in the vertices in clockwise order when viewed from the outside. Clockwise order when viewed from the outside. That's going to become important later on. Okay. All right. Now, there's a problem. These display devices are just grids of pixels, and they're generally organized as a giant array of pixels. In rows and columns, we'll specify row first followed by column, so we'll still have an XY kind of a thing. But when you think about an array, you think about rows and columns, right? Row 5 is higher up in the table than row 20. Row 30 is below row 20, right? So as your row numbers go up, you go down the table. Yes? Please say yes. As you go down the table, row 1, row 2, row 3, row 4, row 5, row 6, you're going down the table, right? If these were in a table, this would be row 1, this would be row 2, this would be row 3, row 4, row 5. You with me? Please say yes. Anybody? Somebody?
Yes, sir.
Okay. All right. Great. But when you are talking about drawing things in an XY coordinate system, ignore that this is labeled Z. Think about this as X. Think about this as Y. Well, what happens? X goes out this way, but Y goes up. That's exactly the opposite. Now, why did humans do this? Because humans are crazy, and we come up with different systems that are the opposite for saying the same thing. Physicists and electrical engineers treat current as flowing in different directions. Why? Well, because they had to guess which way current flowed, and they guessed wrong in electrical engineering, and eventually physicists found out the actual direction of current, and it's the opposite of what the guess was. But since, you had, decades and centuries of people thinking about it one way, they just never changed. When you think about a matrix, you think about a table of rows and columns, and that's exactly the opposite of how mathematicians plot things on X, Y, right? When you plot on X, Y, you go over and up, assuming you've got positive, right? Positive X and positive Y. If you're talking about a matrix, you usually say row column, and higher row numbers go down. So, it's like, why do we do this to ourselves? We do. And we just get so used to it that we don't even think about it anymore. But here we kind of have to think about it, because if you think about display hardware, it's organized like a matrix where you still have X values and you still have Y values, but positive Y goes down, because the Y value is really translated to a row number in a matrix. Okay, so if you want to translate from drawing coordinates to from rendering coordinates from a standard mathematical coordinate system, well, we would expect our origin would be in the middle of the screen, right? At least that would be, and it's be quadrant 1. I've forgotten. Do they go backwards or do they go forward? 1, 2, 3, 4, or is it 1, 2, 3? I've forgotten. But anyway, this is quadrant 1, right? Positive X, positive Y. So if I wanted to, if I had X that went from 0 to 1024, this is 1024 by 768, right? A 4:3, relatively high resolution graphics. And this would sit in some window that would be somewhere on the screen. Well, we're not going to worry about the operating system level where you can move the window around. Let's just worry about what it looks like in the window. Because when you write code, all that code is fixed as if that window is the whole screen, right? So we won't worry about the fact that you can move windows around. We'll just worry about within the window. So within a window, if you're rendering graphics within a window, typically the graphical coordinate system has 0, 0 in the upper left-hand corner, not in the middle where 0, 0 is located normally in a coordinate system. And so you go from 0, 0 to whatever your greatest value is, 1024 in this particular case. So that's our X. We can draw 1,024 dots across. And then vertically, we can draw 768 lines. But it goes, this is line 1, 2, 3, 4, 5, 500, 768. So down is positive. So really what you have to do in your mind, is you have to think, okay, let me do it like this. This is quadrant 1, right? Here's my X and here's my Y. What you do is, in your mind, you flip quadrant 1. It's still quadrant 1. This is still positive X. This is still positive Y. But on the screen, it's going to be drawn like that. See what I'm saying? Some yeses, some yays, some, I have no idea. You look like you're doing some sort of a weird pose, Mike. Anything. I need some reaction from you guys. I asked y'all to run y'all's cameras so I could see y'all's faces not laughing at my dumb jokes. Okay? All righty. Kinda. You can kind of see it. So you would agree, Zach, when you're looking at the graphic system, if my knuckle is the origin here, that would be positive X, that would be positive Y. My fingers are the axis. In fact, in a left-handed system, which is what this is, a left-handed system, this would be positive Z. So positive X, positive Y, positive Z is my thing. So I'm looking from here, bing, right, through the origin, down positive Z with positive X and positive Y like that. Okay. But this is what I have to display it on, a flat pixel grid. So somehow 0, 0, the middle of the screen is where my origin is, okay, in the world coordinate system, in the system that I was talking about when I'm talking about these projections here, right? I'm saying your head is looking at the screen towards the center of the screen. And this is kind of a three-dimensional thing. So here's the screen, here's the XY plane that is coincident with the window, and I imagine myself some distance in front of that window, staring directly at the middle of that window, and my objects in 3 space using perspective projection are drawn onto this screen. Well, what I'm throwing a kink in it and saying the screen doesn't use the same coordinate system. It has 0, 0 in the upper left, and by the way, going down is higher Y. So what this is this is quadrant 1 that's been flipped over, right? It's like quadrant 1 was sitting up here and it fell over. That's exactly what happened. It's quadrant 1, but someone came in with a push, and they pushed quadrant 1 and it fell over. So that's what we have to work with. And you might say, well, but why is it that way, Mike? It's because the graphic hardware is really a matrix of pixels, right? And so people think of rows going down. That's the way it is. And we have to do a little math to convert. So if this point here is 0, 0, what does it need to become? Well, it's halfway across this. So what's half of 1024? Well, 512. So 0 in X is 512. What about Y? Well, Y is even a little bit more complicated. Well, 0 is not so complicated because 0 is halfway. So what's half of 768? Well, that's 384. So 0, 0 in the drawing system is 512, 384 in the display system. And that's where the dot has to be, the pixel has to be lit up. Okay? So let's think about if we had a point that was at, instead of 0, 0, one of you guys has an unmuted mic. If you could mute, that would be great. If you would mute your mic, that would be great. So if I go over 100 and up 100 in our drawing system, that would bring me to 100, 100 in the drawing system. What is 100, 100 in the display system? Well, it's 100 plus 512 will give me 612, so that's the X, right? But for the Y, remember, even though I've got a positive Y here, I'm going up 100, that's actually going to be going down in the hardware system, in the display system. So I'm going to end up subtracting 100 from 384 to give me 284. So 100, 100 in the drawing system is actually 612, 284 in the display system. Well, clearly we need some equations that will take care of that. If you sit down and you think about it, it's not that hard. It turns out that the equation is, well, what's my to get the width, to get X display, to get what the X display is, what's the width of the window divided by 2? Well, the width of this window is 1024, so 1024 divided by 2 is 512, plus whatever your X perspective projection is. Remember, the X, the point that we're drawing here is X perspective, Y perspective. So we've already taken our original points right, in three-dimensional space, our x, y, z, and we've converted them to x perspective, y perspective. So the first thing you got to do is you got to get the three-dimensional point, and you got to use the perspective projection techniques to get the point as a two-dimensional point on the XY plane, and then you have to take that point on the XY plane and convert it to display coordinates. So the formulas for this are using X perspective projection and Y perspective projection. So the X is what's your display window width divided by 2 plus X perspective projection, and your Y display is the display window height, the height, in this case 768, divided by 2 minus the Y perspective. And it's got to be a plus here and a minus here because our Y got flipped over in the hardware, in the display system. So I go through my example here of 100, 100. I said that it needed to be 612 by 284. Well, how did I get that? 1024 over 2 is 512 plus 100, 612. 768 divided by 2 is 384 minus 100. That should be a minus here. See what I mean when I say that I update these notes? So that gives me 284. Does that make sense? Are there any questions about that? Come on. Ask now or forever hold your peace. Does that make sense, what we're doing? I need feedback, peoples.
It makes sense, yeah.
It makes sense. Thank you for being brave enough to speak up. Did it make sense to anyone else? If you're following along in chat, please type right now, yep, or yes, or okay. And if you're not following along, go, hold up. Okay. I got another for the most part. That's good. Okay. So the important thing is I guess I should have bolded these. I like to bold the most important. I like to bold the most important equations. Make that bold, Mike. What's that home? I'll get there eventually. Bold. Thank you. All right. So again, bolded is good because I try to bold the equations that'll definitely go into your code. So you'll obviously need these in your code. Okay. All right. So now you know how to define objects. You know how to define objects, how to build polygons or how to build objects out of collections of polygons, and those polygons out of lists of points. So you know how to do that. You know how to render the points, the vertices, how to project them, and you know that you can draw the polygons in two-dimensional space, draw the lines, the edges between them, okay? I've also showed you how to project those points, right? And then we just talked about before you can actually draw the projected points, you've got to convert to drawing coordinates, from drawing to display coordinates. That is the pixel organization that's used in the window itself. Okay, so sometimes it depends. The answer to your question is yes, Eric, I can see them on the side, but obviously if I'm focused on the screen share, there's less room for your smiling faces. And that just totally, that random question just totally threw me off of what I was talking about. Oh, okay. So now then we've got the objects. We can project the vertices. We can draw the objects in 2D space. And we now know about the display coordinates so that we can actually get pixels on the screen and draw an image. Great. Now what do we do with it? What do we do with our objects? It would be nice if we could manipulate the objects in some way. And that's the next topic. So there are these things called transformations. There are 3 standard kinds of transformations: translation, scaling, and rotation. Most of what you can do to 3-dimensional objects gets down to translation, scaling, and rotation. There are 2 different versions of these transformations. There are 2D versions and there are 3D versions. We're going to start with the 2D versions and talk about them, go over the details, and then we will just extend them to 3D. They extend very easily to 3D. So if you understand them in 2D, it's very easy to move over to 3D. So what are these transformations? There are 3 of them. The first one is translation. Translation deals with moving an object by an arbitrary amount in an arbitrary direction. So let's say that we had this 2-dimensional triangle and I moved it up and slightly over to the right. That's translation. I moved the triangle. It's still the same triangle. It still has the same shape and size. It just moved where it was in space. And that's what translation does. It doesn't affect the size of an object. It doesn't affect the look of the object. It just affects where the object is at. There's also scaling. Scaling is designed to change the size of an object. So if we've got a triangle here, we want to make the triangle bigger or smaller. You can also squeeze an object. You could make it, like, say, bigger in Y, but leave X alone. Or you could make it bigger in X and leave Y alone. So computer graphics are wonderful because we can take a dimension and we can squeeze it, and we can take another dimension and we can stretch it. And we can do all of this using scaling. So in the real world, things are pretty much fixed. You can't do much with them. But in computer graphics, you can take these objects and you can, like I said, squeeze them or stretch them along various dimensions, and you can do that independently. You could be stretching in one dimension and squeezing in another. It's actually quite cool. There's a detail here that I'm skipping over and that we'll talk about in a bit, and that is that scaling can also have a side effect of causing translation. I'm not showing that here, but we'll see that in a minute. There's also rotation. Rotation is when you take an object and you rotate it. So like I took this object and I rotated it 90 degrees counterclockwise. I took this object and I rotated it 90 degrees counterclockwise. So this is the same object, it's just been rotated 90 degrees counterclockwise. Rotation, like scaling, can have side effects, and we'll talk about under what circumstances those side effects can exist. But those are the main 3 things you can do. You can move an object, you can scale it, i.e. you can change its size or squeeze and stretch it, and you can rotate an object. That's the basic 3 operations of computer graphics. Now, just like with our projection equations, translation, scaling, and rotation are linear in nature. And that means that straight lines are transformed to straight lines. And that's important because it'll allow us to apply these transformations to individual vertices of a polygon. So again, if we go back to our pyramid here, I said that when you do a projection, you really just need the 5 vertices that you have to project, and then you can draw the lines in 2-dimensional space, and you get something that would look just like if you projected every single point along every single edge. And I said that saved you orders of magnitude of speed. Well, what if I wanted to take this pyramid and rotate it? Do I have to rotate every single point along? No. I can just rotate the vertices and draw the polygon in 2D space, and you'll get exactly the same thing as if you had rotated every single point along every single edge. So rotation, scaling, and translation, all you have to do is worry about the vertices, and when you draw the thing, it's going to end up looking exactly like you had moved all of the in-between points that make up the edges. So again, that's why I keep stressing these things are linear, straight lines to straight lines. Now, I talked a little bit about the fact that scaling and rotation could have side effects, but that translation doesn't. Translation equations are position independent. The result you get doesn't matter where you start. If I say move a pyramid 5 pixels to the 5 units to the right and 10 units up, it doesn't matter where that object started, it'll move 5 to the right and 10 up. So if I said take this thing and move it, I don't know, like I said, 5 over and 10 up, it's going to be 5 over and 10 up from where it started, no matter where it started. So it's independent. That operation is independent of where it started. Scaling and rotation are dependent. For them to work in a natural way, your object really needs to be centered on the origin. For scaling to work in a natural way and for rotation to work in a natural way, the objects need to be centered. And we'll talk about that. So let's look at some equations. Here are the equations for 2D translation, and they are very, very simple. If I have an X, and remember the way we're going to be using these things, if I have an X and a Y, and I want to translate by some amount, Tx is the amount that I want to translate in X, and Ty is the amount that I want to translate in Y. So really all you do is you take your original point, your xy, and you add the translation amount in X and the translation amount in Y, and that gives you your new translated point, translated X and translated Y. So again, Tx is the distance the X coordinate will be shifted. Ty is the distance the Y coordinate will be shifted. So what does a positive Tx do? Well, a positive Tx shifts to the right, and a negative Tx shifts to the left. What about Ty? A Ty, positive Ty shifts up, and negative Ty shifts down in the drawing coordinate system, right? In the system in which the origin is centered in the middle of the screen, okay? And so we need to show that this really does work. So here's an example. I'm going to translate 1 over in X and 2 up in Y. And here's a little object, a little pyramid, sorry, a little triangle, point 1, 1, 2, 2, and 3, 1. And so if I apply the equations, right, if x1, y1 is 1, 1, then it's 1 plus 1 is 2, and 1 plus 2 is 3. So 1, 1 becomes 2, 3. This 1, 1 becomes 2, 3 because it's add 1 to x, add 2 to y, 2, 3. Okay? How about 0.22? Add 1 to x, add 2 to y. So 2 plus 1 is 3, 2 plus 2 is 4, 2, 2 becomes 3, 4. How about 3, 1? Same sort of thing. Add 1 to 3, that'll give you 4. Add 2 to 1, that'll give you 3. So 3, 1 becomes 4, 3. And so if I know that my polygon is aligned from point 1 to point 2, and from point 2 to point 3, and from point 3 back to point 1, well, once I've done that translation, I can just draw these lines shown in green dashed, and I will get exactly the same object. I really only had to translate the 3 vertices, right? And then do line draw commands, and you get the same thing as if all of the in-between points were translated, because they are. Does that make sense? Let me see some yeses or some hell yeses.
Yep,
or
makes sense.
Yay, okay. All right, good, okay. You guys are just so non-reactive. I'm asking these questions to make sure you're staying awake, and unfortunately, I'm not getting much feedback. So that makes me go, are they really staying awake over there? Don't be embarrassed to type yes in the chat. That's the reason it's there, so you can type yes in the chat. Okay. And I can see your faces here, by the way, even though I'm screen sharing. I see some of you look bored. Some of you look happy. Some of you look like you're in space. And yes, I'm talking to you, Landon. Okay. Okay. There's a storm going on? Okay. All right. It's okay, guys. It's okay. Just want to make sure we're all staying awake. Because you're going to be having to write these programming assignments, and that means you're going to have to know how to apply all of these formulas. Okay. So that was that. That's pretty short and sweet. Let's move over to scaling. Scaling is also fairly straightforward. The purpose of scaling is to change the size of an object. Okay. Now, normally, like I said, normally we think about when we want to change the size of an object, we normally think about, well, I want to double it in size, or I want to cut it in half by 50%. So we call that uniform scaling. Okay. Uniform in that in all dimensions we're either expanding by some positive number or we're contracting. But like I said, there's non-uniform scaling where you're changing by one factor in X and maybe another factor in Y, and if we're talking 3D, you have another factor in Z. But uniform scaling, you're changing all of them by the same amount, essentially. So in uniform scaling, we have some uniform scale factor, but call it S for scale. But you know, your scale factor in X could be different than your scale factor in Y. That's possible. So what are the equations? Okay. Well, the equations for two-dimensional scaling are simply S scaled is your X value times your scale factor in X. And Y scaled is simply your Y value times your scale factor in Y. Okay. So so the difference, right? Remember we just looked at translation, and instead of multiplication, it was addition. Right? Well, for scaling, instead of addition, it's multiplication. That's the only difference. Okay. So in translation, you had a translation factor where you were adding it to the X and Y. In scaling, you have a scale factor that you're multiplying to the X and the Y. So Normally, SX and SY are the same when you're doing uniform scaling, but they could be different, right? So SX is the scale factor along the X horizontal dimension, and SY is the scale factor along the Y vertical dimension. Okay, so how does this work? Well, if the scale factor is bigger than 1, it's going to increase the object along that dimension. So if SX is greater than 1, it's going to increase the size of the object in X, while if SY is greater than 1, it's going to increase the size of the object in Y. What happens if the scale factor is less than 1? Well, scale factors that are less than 1, that are fractional, like 0.5 or 0.25, they decrease the size of the object in the specified direction. Now, here's the difference between scaling, what we're looking at now, and translation. In translation, you had positive translation factors and negative translation factors. Positive went to the right, negative went to the left, or up and down if you're talking about Y. Normally, scale factors are considered to be greater than 0. Normally, scale factors are considered to be greater than 0. If a scale factor is greater than 1, it's going to increase the size of something. If a scale factor is greater than 0 but less than 1, it's going to decrease the size. Okay? All right. So let's look at uniform scaling and see what happens. So here's our same little triangle, 1, 1, 2, 2, 3, 1, and we apply a scale factor of 1.5. We're not going to double it in size, we're going to increase its size by 50%. And if you look at this puppy and you look at this puppy, the blue and the green is about 1.5 times along each dimension bigger than the original. In fact, it's exactly 1.5. This was, the base here was a 2 in length, right? Well, the base here is from 1.5 to 4.5, so it's 3. So it was 2 here, it's 3 here, that's 1.5, right? So along each of the dimensions, we've increased by 1.5. And here's the math that shows what we did. 1, 1 is 1.5, 1.5. 2, 2 is 3, 3. 3, 1 is 4.5, 1.5. And so that's that, and we plot it and we get this thing. So what's wrong with what the scale did?
The object moved?
The object moved, right? I didn't want it to move. I wasn't trying to translate it. I was trying to make it bigger. Why did it move? Well, to understand it, in your mind, think about the fact that you're staring at point 0, 0, okay? And when I make the object bigger, it slides further towards your peripheral vision. So it moves. It'll make even more sense when we do this in 3D. Okay, when we look at three-dimensional objects, think about this not as a triangle, but think about it as the front-facing side of a pyramid. So if I've got a pyramid here and I'm staring at 0, 0, and I move in closer, I move my nose in closer to 0, 0, the front, where that pyramid is, it'll look bigger because I'm getting closer. But since I'm not staring at the middle of the thing, it'll appear to shift towards my peripheral vision. That's essentially what's happening. Okay, so we're moving it. We're increasing the size, but we're increasing the size relative to this point right here. And if you're having trouble seeing it, think about if I didn't have one pyramid, but I had 4. I had this one, I had one over here, I had one down here, and I had one down here. Well, think about all those 4 objects as connected together somehow, And if, again, if I move in on 0, 0, they're going to all get bigger, but they're going to shift towards your peripheral vision. So everything is fixed about the origin. Now, this anomaly will go away if we take an object, like here's another object, here's our blue object, right? And this object is centered on the origin. The visual center of this object is the origin. Well, let's say that I want to shrink the object to 0.5. Well, it moves from the blue object to the green object. Green object's the new object. And you can see that the green object is smaller, but it didn't move. It didn't move because it was already centered on the origin. So that's the secret. If your object is centered on the origin, it won't move when you scale it. If the object is not centered on the origin, it will still scale properly, but it will move. If you're scaling it to get bigger, it will move away from the origin. If you're scaling it to get smaller, it will move towards the origin. Okay. So let's see if we can summarize what's going on here. So first of all, scale factors are generally assumed to be positive. Unlike with translation factors, where they can be both positive and negative, with scaling factors, they're always assumed to be positive. Now, what happens if you were to set your x and your y to 0? You tell me, what will happen if I try to scale an object and I make my scale factor 0? Well, you can read, just like I can read. Basically, this is the black hole operation, right? Where the object falls into a black hole if you do this, because what will happen is scaling by 0 will reduce the object to a point at the origin. It falls into a black hole, essentially, because all of the vertices, no matter what they were originally, become 0. Because anything times 0 is 0, and you're multiplying all your x values by 0 and all your y values by 0. So it's like as your scale factors get closer to 0, you got an object, and it's getting smaller and smaller and smaller as your fractions for your, it's like, okay, here's the object, here's at 0.5 the object, here's at 0.25 the object, here's at 125 the object, and eventually when you get to 0, the whole thing is reduced to a black hole point in the center. So that's what a scale factor of 0 does. It causes your object to reduce to a point. How about a scale factor of 1? What does that do? Nothing. Multiplying all of your x values by 1 and all of your y values by 1 doesn't change them at all. So a scale factor of 1 leaves the object completely unchanged. Scale factors greater than 1 increase the size of the object, as we already said. So if you had uniform scaling with a factor of 2, that would double the object size. It would double the length of the object along each of the 2 dimensions, since we're doing 2-dimensional here. Okay? If the scale factor is greater than 0 but less than 1, in other words, it's a fraction, like that's going to cause the object to shrink. So if the fraction is 0.5, 1/2, that will shrink the object in half along each of the dimensions. Remember that the scale factors can be independent. Nothing says that x and y have to equal the same thing. They don't have to. And always remember, if your object is not centered on the origin, the equations for scaling have the side effect of translating the object as you scale it. If your scale factor is greater than 1, it's going to move away from the origin. If your scale factor is a fraction between 0 and 1, it'll move towards the origin. And that's scaling. So questions. We answered Eric's. Andrew, we're going to talk about how to get rid of this problem when we do assignment 2. Okay. For assignment 1, we're not going to worry about. We're going to treat it as a feature rather than a bug, that objects that are not centered at the origin move as well as change sizes. Okay? All right. So that got us through all the material we wanted to get through today. On Monday, we'll talk about 2D rotation. But again, if you want to skip ahead, we're going to go through all of this, and it's all important. But if you want to look at page, whatever page this is, page 14, this is all of the equations for the 3D transformations that you'll need. So those equations plus the equations for perspective projection, right, plus the equations for perspective projection, these equations, plus the equations for converting to display coordinates, these two equations. That's really all you need to do assignment 1. Okay? All right. So at this point, I'm going to kill the recording. I'll see you guys on Monday. If you have additional questions, please feel free to stick around. After I kill the recording, I'll answer any questions you might have. Okay? All right. See you guys on Monday.